Hello, welcome to the very first lesson in organic chemistry, all about the most simple alkyl molecules. Now, first we have to kind of talk about what organic chemistry is. So, organic chemistry is the chemistry of carbon, and you may ask, why carbon? There's 118 elements. Why did nature pick carbon? Well, carbon has 4 valence electrons. And remember the octet rule, all atoms want to have 8 valence electrons. So carbon is going to try to bond 4 more times. So if you look at a picture of a a Lewis diagram, it would look like this, where we have carbon with 1, 2, 3, 4 electrons. So what happens here is that carbon will attempt to bond with other elements. So let's say we have an X, an A, an L, and I'm trying to think of elements that are not letters, D. So it'll try to bond with different atoms in order to get its full 8. Now, some of these may be other carbon atoms, and when that happens, we get a big, we can get networks, we can get chains, we can get all kinds of different things. So a chain would look like a bunch of carbons linked together, kind of like this in a line. These chains can actually, you can bond chains to other chains, so it would look something like this. It can get pretty crazy. So it's all because of carbon's small radius and its electronegativity and the fact that it's willing to bond 4 times. The most simplest of all organic molecules is called methane. You may have heard of it before. It's a big culprit in global warming. And it looks like this. You have a carbon that starts with its 4 valence electrons, and then it will bond to 4 hydrogens. So this hydrogen comes in and they say, hey, I'll share one with you if you share one with me. And then this becomes a single covalent bond. And that happens 3 more times. We get a bond here. Remember, there's 2 electrons in every bond. I'll share one with you if you share one with me. So that is our simplest organic molecule. Now, we can also form rings where they literally form a ring. And then we also have networks, which is kind of where they almost start making like honeycomb shapes, and they sort of make sheets. Sometimes those sheets will wrap around and create a sphere. It gets very crazy. So the chemistry of carbon is called organic chemistry. And organic kind of sounds like, you may think of like produce, like organic broccoli, right? Well, organic technically means something that is alive, right? You and I, we are organic beings, where our phone is not organic because it's man-made, right? There's no life to it. So we, as far as we know, all life requires carbon. So that's where those 2 terms kind of overlap, is carbon and organic. You need carbon to have life. Organic means life. So they call it organic chemistry. And then when you get to college and you study just organic chemistry, if you're a chemist or if you are going to study medicine, usually it gets shortened down to orgo. Some people call it OChem, which is not, it's orgo. But here you go. The only qualification for something to be an organic molecule is that it contains both carbon and hydrogen. They can also contain other things, but carbon and hydrogen is the bare minimum, just like methane. It's just carbon and 4 hydrogens. So a lot of people ask, is carbon dioxide an organic molecule? And to that, the answer is no, because there is no hydrogen. It's just carbon and oxygen. So it's a very common carbon compound. Try to say that 10 times fast. But there's no hydrogen, so it is technically called inorganic. You put in front of any word and it means the opposite. So this would mean that it is not organic. So we have a group of chemists. I guess they just sit in office and brainstorm rules for all of us to follow, but they are called IUPAC, which is the International Union of Pure and Applied Chemistry. And they have come up with a system for naming molecules so that if I write down the name of a molecule, anybody who knows the codes can take that name and turn it into an accurate picture. Prior to this, we were kind of naming stuff with a common name. For instance, citric acid. The name citric acid doesn't tell you anything about what the molecule looks like. It has its common name is citric acid, and then it has a systematic or an IUPAC name, which follows all the rules. I don't know what it is technically. I do know that the systematic name for water is dihydrogen monoxide. That's not the organic naming system, but IUPAC still came up with that name based on a system. So the point of the system is just so that we can communicate the name and what it looks like. And that's pretty much it. So we have carbons that can form chains. These are the simplest things. They are the easiest to name. And that's really the start for everything for high school chemistry. So a chain, like I showed you before, is carbons that are all strung together in a line. And it's important to note that these carbon molecules can actually like wiggle in space. And the bigger they are, the more they wiggle. This is, if you remember all the way back from intermolecular forces, London dispersion forces or van der Waals forces, sometimes they're just called dispersion forces. Really what that means is that the more electrons you have, the bigger that cloud is that can get warped. I believe our lesson number for that was 5.2 or 3. I don't remember exactly. But the bigger a molecule is, the longer its dipole moment when it's nonpolar because of its wiggling. So these carbon molecules can also wiggle, and the bigger they are, the more they wiggle. So sometimes it's not a straight line. Sometimes it's actually a jagged line or a zigzag. So there are 2 types of super basic, simple organic molecules, and those are called hydrocarbons. Hydrocarbons, obviously, are made out of hydrogen and carbon, like methane that I showed you. That is a hydrocarbon. Now, a saturated hydrocarbon has the maximum number of hydrogens on that carbon, meaning that there are no double bonds and there are no triple bonds. I kind of want to show you a picture of this. Let's go back here. We have, oops. Sorry, I'm not very good with this app here. So if we were to look at a saturated hydrocarbon, let's say we were looking at butane, that's lighter fluid, right? Most of these do appear in your real life. So butane is 4 carbons in a chain, and this is considered saturated because each of these carbons has the maximum number of hydrogens attached to it, meaning that every carbon gets 4 single bonds. These get really tedious to draw. I'm sorry, this also looks really ugly. I'm drawing with like a stylus, so I'm not very good at this. But this is butane because it has the maximum number of single bonds, and this would be a saturated hydrocarbon. Saturated full. Remember saturated solutions, they are full of solute. A saturated hydrocarbon is full of hydrogen. Next, we have unsaturated stuff. So let me just draw that in a different color. I'm going to draw butene. So butene, the ENE at the end of that indicates that my program is lagging a little bit. I'm sorry, I'm trying to show you the tippy top there. Okay, so butene, the but is going to tell me that it has 4 carbons. Let's say this is 2-butene. So I want my double bond to be on carbon 2. So it's a little slow here. Come on, baby. So if you notice, remember we said before that every carbon is going to try to make 4 bonds. Well, 2 of my carbons here already have 3 bonds. Do you see this? This carbon right here, the second carbon has a single bond right there and it has a double bond right there. So it already has 3, meaning it can only make one more bond. So instead of it getting a hydrogen on the top and a hydrogen on the bottom, it's only going to get 1. I'm going to put it on the bottom just for the sake of space here, but realistically, oh, you can't even see it. Realistically, it could have gone either way. Usually we'll draw one on the top and one on the bottom just because those hydrogens are going to try to repel each other just because everybody likes to have their own space. So both of these carbons here have the maximum amount of bonds, even though they only are attached to 3 atoms each. So this is something that would be considered unsaturated. Oh boy, this is very ugly writing. I apologize. And then each of my carbons on the end would also get all of their hydrogens. So this would be considered an unsaturated because it's not full of hydrogens. And I'm going to have to zoom out again. So it would look like this. So I hope that you can see the difference here. Once you start putting multiple bonds, meaning a double or a triple bond, you in turn have to start removing hydrogen. So that molecule is not full of hydrogens anymore, and therefore it's considered unsaturated. Okay. Here's where I am. So let's present and go to the next slide. Okay, so there are 3 types of carbon chains. So if we have a carbon chain that is all single bonds, like that red molecule I just showed you, we would specifically call that an alkane. Then, if we have at least one double bond, we're going to change the suffix or the ending of that word to alkene, E-N-E, and that, remember the IUPAC people? When you hear the name, you should be able to kind of picture it. "-ene" in your ear tells you that you should see a double bond somewhere in that molecule. And then last we have alkynes. And alkynes, the Y-N-E ending tells you that there's a triple bond somewhere within that molecule. And these are called a homologous series. So like a carbon chain with one carbon would be called an alkane. Specifically, it would be methane. If you have 2 carbons, it would be ethane. Take out the M. If you had 3 carbons, it would be propane. 4 it would be butane. That is called a homologous series. And we'll get into that in a little bit. So we should be able to name any molecule by looking at it the same way a name can give us a picture can give us a name. So this is on the assumption that you are looking for a name from a picture. I'm sorry, I'm trying to work on this. So we are going to find the longest string of carbons, and then we are going to name that using a prefix. And there's prefixes on your reference table. Then we are going to look at the types of bonds and figure out what suffix goes on that. So here are our prefixes. When I have 1 carbon in my chain, it is a meth thing. So it could be methane, or if I'm not even going to go any further than that. So methane is a culprit in global warming or climate change. It causes the greenhouse effect. So it's more or less in the warming aspect of everything. Then we have ethane. Propane is in a barbecue, like those tanks people use them for cooking and camping. Butane is in a lighter. Pentane. We have hexane, heptane. Octane is like a component of gasoline. We have nonane and decane. Okay, so that's a prefix. We can also have, we can have methane, we can have ethene, propene, butene, et cetera, et cetera. So those are the prefixes that go on, and when we see or hear a prefix, we can imagine how many carbons are going to be in our picture. So I want to kind of just teach you by example, because I honestly think that's the best way to do this. So we're going to pop over here, and I'm going to start drawing pictures. So let's say I have this molecule. Okay, as I'm drawing the hydrogens, and I'm sure this program is really slow. Yep, I'm almost done, and it has hardly started. So here, you should be able to look at this molecule and kind of figure out what's going on here. So the very first step is to count the number of carbons. So what I like to do is draw a line through them because sometimes these chains can bend. So right here, I have 1, 2, 3, 4, 5 carbons. So I know that I need pent somewhere in the name of this molecule to indicate that there are 5 carbons here. Okay, and then I can look at this molecule and identify that I have all single bonds between my carbons. My carbon chain is made of all single bonds. And if you remember, alkanes are the molecules that have all single bonds. So this here would be pentane. 5 carbons all bonded together by single bonds. That's what pentane means. So when you see the name, you should be able to picture this molecule. Probably not now, but at some point you should be able to do that. And that is the point of the IUPAC naming system, is so that chemists can communicate with each other without having to send a picture, because citric acid isn't going to tell you what the molecule looks like, but pentane can tell you exactly what it looks like. Does that make sense? Okay, I hope it does, because you can't answer me. The next thing I want to draw. Let's do this. You see how it bent there? I'm going to draw all of my hydrogens. Remember, each carbon needs to have 4 bonds in total. I'm sorry, some of these H's just look like +1, and it's kind of hurting my brain. It's far easier to teach this one in person. Okay, so here's my molecule. So when I count, I like to literally draw a line through all of my carbons to make sure that I didn't miss any, because sometimes these things get twisty and curvy. So in this case, I usually like to go from left to right. It technically doesn't matter right now. So I'm going to draw a line through all my carbons. Boop. They are allowed to twist and turn. So if I were to count this, I would have 1, 2, 3, 4, 5, 6 carbons. If you look at the reference table, there is a prefix for 6 carbons, and that is hex. Hex tells you there are 6 carbons. Now I need to look at my bonds. If I look at my bonds, this tells me that I have all single bonds. All single bonds means this would be hexane. I have all single bonds, 6 carbons attached. Now, this is allowed to twist because in real life, hexane wiggles. All of these bonds are bending. So this is just like we took a picture of it and it was snapped in time. This is what it looks like now. And in 2 seconds from now, it could be a straight line. And then a split second later, it can be like a mountain range all zigzagged. It's bending. So we just took a quick picture and this is what it wound up looking like. So don't be afraid of the curviness. Next, I want to get into some unsaturated hydrocarbons, meaning we're looking at multiple bonds. So let's say we have 1, 2, 3, just like this. So this is 3 carbons. Let me draw my hydrogens. Technically, these hydrogens do go out on a diagonal, and that's because of the spacing between them. I'm just going to put this hydrogen on the bottom. It could have been the top or the bottom. Not only do these molecules wiggle in space, but they'll also flip around, and sometimes they'll point at you and they go like back into the page. For the purposes of high school chemistry, I think a straight line is just fine, but it is something to be mindful of if you are going further in chemistry than just high school. I don't know if you saw the time there. It's 4 o'clock. My dog eats at 5, so he's going to cry in the background for the next hour. So this is a molecule right here. And the first step always is to find the longest attachment of carbons. So in this case, I'm sorry, this kind of looks like a double bond, even though it's not. That's supposed to be a single bond. My apologies. Hydrogen can only make one bond. Remember, it's following the duet rule. So here, my longest string of carbons goes right here. That is 1, 2, 3. So I have 3 carbons here. If you look on the reference table, 3 carbons, the prefix for that is prop. I know it looks like prop, but we pronounce it prop. So this is prop because there's 3 carbons. And then if I'm looking at my bonds, I find that right here we have a double bond, which means I need "ene" somewhere inside my name. Okay, so propene is going to tell you that I have 3 carbons with a double bond. Okay, now for propene, it can be this simple. I want to show you another example because it's going to get a touch more complex. And then after this touch, we're pretty much done because that's as easy. That is as difficult as it gets. So here we have propene, 3 carbons, and there's a double bond in there. But if I were to look at something like this, and then I attach my hydrogens, of course, making sure every carbon gets 4 bonds. That honestly is probably the biggest error when people are drawing molecules, is that they would give this carbon a hydrogen on top and a hydrogen on the bottom, which totals 5 bonds, and then that carbon is not a happy carbon. Hey, Koopy, why don't you stop crying? Mommy's busy. So right here we have 4 carbons in our chain, right? Let's draw the line. Right here, we have 1, 2, 3, and 4. Perfect. So if I have 4 carbons, then my prefix is bute. Not but, it's bute. So if I were to look at this, I know, hey, look, there is a double bond in here. So that means I need to have an "ene" in here, right? This is going to be butene, but this doesn't actually tell me where the double bond is. It just tells me that a double bond is there, okay? Having a double bond in the middle of the molecule versus this area on the end will change the boiling point, the melting point, the strength of the intermolecular force. It changes the way that the butenes would interact with each other and with their environment. We have said a billion times this school year that the structure of molecules matters, where the electrons are matters. That's why we study all of this. So this butene would be different from a butene. The butene that has a double bond in the middle is different from a butene that has a double bond on either end. So I would specifically say that this is 2-butene, and this is where it comes from. I'm going to redraw this in a little fresh area. And I'm going to leave out the hydrogens for now, just so we can see the difference. So this right here that I'm drawing is 1-butene. Sorry for the handwriting. 1-butene means that my double bond is attached to carbon 1. In your brain, imagine that's full of hydrogens. 1-butene could also look like this. Remember, these molecules flip around in space. This is the same thing. It's just like going from here to here. They're the same thing. It's just flipped. But 2-butene is different. 2-butene, oops, would look like this. And any way you flip that, the picture would look like the green picture I have here. So there is a difference here. Where the double bond is matters. So I have to give it an address. We put the number in front to tell you which carbon this special thing is attached to. And the special thing in this case would be the double bond. So what happens is we number all of our carbons. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. So the way that we assign these numbers is that the number is going to get we want the number to be the lowest number possible. Okay, so if you look at this very first 1-butene, this double bond right here is attached to carbon 1 and carbon 2. 1 is the lower number there. That's why it's called 1-butene. In this case, which is the same picture, it would be 3-butene, right? But 3-butene is not the same as 1-butene. It is the same as 1-butene, and here's why. When we number these things in the directions I told you to number it both forwards and backwards, if I number it forwards and backwards, it accounts for the fact that these molecules can flip. And the picture was just drawn silly. Like the snapshot that we took wasn't the best possible snapshot for us to be taking. So when you number it forwards and backwards, you account for the fact that it'll flip on you. So if you look on the blue system for this here, I would have gotten 3-butene. But if I look at the red system, I get 1-butene. Both of these molecules are 1-butene. And this one is just flipped over. I'm hoping this is making sense. And then for this baby here, the green one, if I number this backwards to say, hey, I wonder if it flipped on me. Any which way, this double bond is between carbons 2 and 3, or it's between carbons 2 and 3, and 2 is the lowest possible number. So the address that I would give this baby is 2-butene. I hope that makes sense. So I want to draw a picture for you and give you a minute to try to figure out if you can name it on your own. Oops, that looks ugly. Boop, boop, boop. Okay, just imagine that looks pretty. Okay, that's the gist of the molecule. I'm going to fill in the hydrogens in silence so that you can attempt to name this. If you need more time, pause it. Okay, there's our molecule. Notice that there's no hydrogens in this area because this carbon has 1 bond here, 3 over there. That totals 4. This carbon has 1 here, 3 there. That totals 4. They can only bond 4 times. Okay, I'm going to explain it. So if you need more time, pause it here. If I look at this molecule, this has 1, 2, 3, 4, 5 carbons in total. For a fact, I know that there is going to be pent inside this name. I'm going to number it both forwards and backwards. Because I know I have this special triple bond right here, which means I need to add an "-ine" ending to the name of my molecule. So this is pentyne. Pentyne tells you that there's 5 carbons and there's a triple bond somewhere, but it doesn't specifically tell you where the triple bond is. The triple bond could have been on the end of the molecule, or it could have been somewhere in the middle, and it matters because the location of the triple bond, you get a bunch of electrons crammed into one spot. It's a very negative area of the molecule. So it will affect its intermolecular forces, its boiling point, melting point, how it interacts, basically everything about it, all of its physical and chemical properties. They are different than if the triple bond had been somewhere on the end. So I need to give the location of this molecule, and I give it with a number. I give it its carbon number. So because I have numbered this molecule both forwards and backwards, what that does is it accounts for the fact that these molecules can flip around. Okay, so on my top numbering system, the triple bond came between carbons 3 and 4, and on my lower number system, the triple bond came between carbons 2 and 3. So out of those 4 numbers, I want to assign the lowest number possible, meaning that this molecule is called 2-pentyne. Did you get it? I hope so. That is as crazy as it gets, really, in terms of simple alkyl molecules. Next lesson is about chains that attach to other chains, and future lessons are about like fluorines and chlorines and other types of atoms that get stuck onto these molecules. Those are called functional groups. I would like to give maybe one more example. In terms of high school chemistry, double and triple bonds don't really show up on the same molecule. There are a lot more rules for when things like that happen. I just want to show you one more thing. Okay, so let's say I have a molecule like this. I'm sorry, I'm trying to be careful with my hydrogens to make sure they look like hydrogens. And as soon as I say that, my hydrogens get uglier. So let's say I have this molecule. If we were to go through and count, let's do 2 different colors this time. We have 1, 2, 3, 4, 5 carbons in my chain on my blue numbering system. And let's use red. Red is a little bit more different. Here we have 1, 2, 3, 4, and 5. Now, we have to commit to a number system. We can't mix and match blue numbers and red numbers. So if we pick the blue system, we have to stick with the blue. If we have the red, we have to stick with the red. The idea is that we want all of our numbers to be as low as possible. Okay, so I know I have 5 carbons here, so pent is going in the name. I know that I have double bonds. Bonds. So that means I'm getting an ene somewhere in my name, right? Pentene. Now I have to indicate that there are 2 double bonds, and I have to tell you where they are. Well, I can indicate that there's 2 double bonds by using 2 numbers. You with me? So this baby, I have a double bond here. It's between carbons 1 and 2. I have a double bond here. It's between carbons 2 and 3. So I can select 1 and 2. 1 would go with this bond and 2 would go with that bond. Or I could choose, because let's see, I would not choose 5. Hold up. Is there an undo button? Undo. Perfect. This bond on the left side is between carbons 4 and 5. So I would choose 4 to identify that bond, and I would use 3 to identify that bond, right? You with me? Is it writing? Hello, program. Catch up. There we go. So I can choose 1 and 2, or I can choose 3 and 4. 1 and 2 are my smallest numbers. So I am going to call this, come on, let's do the blue. Let's keep this color coordinated. I would call this 1, 2 pentene. The 1 and the 2 tells me the location of my double bonds. Okay. Sometimes we have more than one fancy thing on our molecules. When we have more than one thing, we need more than one number. Okay. That's really the gist of it. I don't want this to drag on for a million years. This is really just the introduction. I definitely think that this is something that you learn by practicing it, which is very difficult to do in an online setting, especially when this is a one-way conversation. So that's it. If you have any questions, leave a comment. I will do my best to get back to you. And that is literally it. Okay, goodbye.